Okay, well, I just have a very exciting announcement this morning. Um, Today is the first day that it's going to drop below 100 degrees. Since you've been in school this semester, right? Has it been 100 degrees the whole time?
It's gonna drop fast too, like Halloween and stuff.
What?
It drops pretty fast, I feel like afterwards. Like Halloween.
Oh, it's supposed to be a lot colder. I've lived here for like 30 years and I think it's never been this hot. I might be forgetting.
Yeah, we broke like a record of like most consecutive days over 100 days. That's weird.
I believe it. And especially this late fall. I've never seen this before. So, well, I was thinking maybe we're heading into the Hadean Ian, but I guess maybe not. But we all like the seasons. Like right now is if we weren't in Tucson, it would be the turning of the leaves and harvest time, and then snow in winter, and then blossoms in spring and growth of crops in summer. And then night and day are also amazing. I love falling asleep at night, and then usually I enjoy waking up in the morning to a fresh new day. So, we have lots of cycles on the earth. Even a new year, it's a chance to start over, New Year's resolutions. And so, it might not have always been like this. So, there might not have always been seasons and days and years as we know them in the long history of climate on our planet. And a possible indication of this is that there were equatorial glaciations at the beginning and the end of the Proterozoic eon. And in 1975, George Williams, who's a fellow of the Geological Society of America, the Geological Society of Australia, and the Australian Academy of Sciences, proposed that a greater tilt of Earth's axis would explain the equatorial glaciations. So there was glaciations at the equator, but not at the poles. One explanation for the equatorial glaciations, do you guys know what that is? It's the most popular explanation. Snowball Earth, the entire Earth was covered in ice. So that's another possible explanation for the equatorial glaciations. But if the axis of the Earth was pointed towards the sun, then we wouldn't have had the days and nights like we have today. We would have like a half a year of day and a half a year of night. And likewise, a half a year of an extremely hot summer where it's light all the time, and then a half a year of an extremely cold winter where it's night all the time. So, anyway, this lecture will mostly be on that topic, but we'll also look at other issues related to early climates and our present climate. Okay, so as with ancient meteorites being the key to understanding the solar system, the key to understanding the history of the Earth is ancient rocks. And so during the 17th to 20th centuries, scientists gradually divided or defined geologic time, culminating in the modern geologic time scale. And then in this chapter, we're going to look at these two eons here, which were from 3.85 to 2.45 billion years ago. That's what GA means. And then 2.45 and to 550 million years ago. So we have the early one was the Archean. And although there's a few rocks older than the Archean, um, the first geologic record we have really is of the Archean Eon. So we'll be looking at some of those rocks. And there's a quandary in the early Archean due to the interpretations of the rocks. So they can tell a lot about the Earth by interpreting the rocks. And also the understanding of the history of the sun. So according to George Fuellner, who's a climate research scientist at the Potsdam Institute for Climate Impact Research, the what's called the faint young sun paradox is the most fundamental problem in paleoclimatology. And so scientists know that the sun was 20% cooler at the beginning of the Archean. And remember, we're in the Goldilocks zone now, but we wouldn't have been if the sun was 20% cooler. The whole Earth should have been frozen over. And so, but there's evidence in Archean geologic formations that the oceans were at least 26 degrees centigrade, the surface of the ocean, and ranged up to 85 degrees centigrade. So, you know, frozen is 0 degrees centigrade. So that's why it's such a problem. They can't put together the idea that the sun was colder, but the Earth's oceans were hot. One proposed solution is that the atmosphere had extremely high global warming potential, but all of the proposed atmospheric compositions either have chemical problems or they insufficiently alter the Earth's energy balance to cause liquid water in the oceans. There's another solution which to the faint young sun paradox, which is that the Earth's axis would tilt toward the sun. And if that was the case, then the sun would be on that side of the planet for like 5 months at a time, and then the waters would become heated up. And then in that same model, glaciers don't form on the opposite side from the sun. There's just not enough time. And also there's not a lot of water in the atmosphere. So those are the two solutions, but at this time they really haven't resolved it, mostly because they don't accept the idea that the Earth's axis was pointed towards the sun. The snowball Earth hypothesis, which is shown here, the entire Earth was a snowball. Well, you know, the surface. This is the most popular solution at this time among geologists. The idea that the Earth's axis was pointed towards the sun and then tipped up to our current 23-degree angle of obliquity. That's the one I described before. That's not so popular, although that would solve the faint young sun paradox. Okay, so we'll talk about the early Archean, then we'll talk about the Proterozoic Eon, the two solutions to the equatorial glaciations. And then finally, we have the Phanerozoic Eon, which is our current eon, which began just before the Cambrian. And since then, the climate has pretty much been unpleasant. You know, it's only fluctuated by like 10 degrees centigrade. Although, as you can see in this graph here of the last 2,000 years, we have this current climate spike going on, which really is becoming apparent with these temperatures we're seeing in Arizona this year. I mean, you can't just use anecdotal evidence, but all over the place, there's hot temperatures. And who knows, maybe this hurricane is caused by global warming. So there's just a lot of evidence that humans are altering the global energy balance with carbon dioxide and methane that they're putting into the atmosphere. Okay, and then we'll briefly touch on philosophical and religious perspectives on climate. And then we'll end with Mr. Guyot, or Dr. Guyot. Okay. So as usual, a great discovery was made by somebody who was looking at the data and thinking about it. So in the 18th century, there was a geologist an Italian miner named Giovanni Arduino. And he drew this picture here and took all these notes, made all these notes. But he realized that the geologic layers in the Alps, which he drew in this picture, were laid down on top of each other over a long period. And he realized they could not possibly have been laid down in 6,000 years, as most people thought at the time. They thought the Earth was 6,000 years old, or about thereabouts. And he was the first person to define periods in Earth's history. There had been a guy before him, I forget what his name was, and he realized that geologic layers were laid on top of each other, but he didn't alter like the 6,000 years idea. But Giovanni Arduino was the first one to say that the geologic formations were laid down over long periods of time. And he classified them as primary, which were volcanic and metamorphic rock at the base of the Alps. So those were the lowest. Then above that, he had the secondary, which included hard sedimentary rocks. And then the tertiary was at the top and included softer alluvium. So up until the 20th century, people still use those terms to describe the geologic ages. But the modern geologic scale replaced Arduino's scale. For instance, the tertiary period is now called the Cenozoic era. But if you ever read about the tertiary, you know it's the Cenozoic era. Okay. And then about a century later, it seems like somebody made a discovery every century. About a century later, William Smith was the next to make a significant advance in the geologic timescale. So he really wasn't looking for geologic information. He was a surveyor in England for mines and canals. But as he was, walking around surveying, especially for mines, one thing he noticed that this same coal seam here was found throughout England in different places. And he also noticed that there were other layers that repeated. And so his other job was surveying canals. And in that job, he was just walking long distances and looking at the land surface. And when he was doing this, he noticed that there were similar layers. And so he was trying to figure out whether the similar formations were related or the same. And one thing he noticed was that he could identify the same layers by the type of fossils. So here's like the type of fossils he might have seen. And then he realized that the species and fossils changed over time in geologic time. And so he realized that he could use the fossils to date the geologic layers. And you can even do that across oceans because, the same oceans were covering England and covering, France at the time, or that would be the closest one to him. And so he developed what was called the Universal Geological Timescale based on fossils. He also realized in his work that the geologic layers were tilted on their side like this, just like Arduino had in the previous picture. And he realized, or he proposed, that uneven uplift had uplifted the geologic layers, such as we have in Arizona. We've had uplift, which is why the Colorado Plateau, where the Grand Canyon is, although it was previously in a tropical zone, is like 5,000 feet high now. So at the time of William Smith, they realized like you could walk across these layers and you could see that there was all these sedimentary layers that formed year after year after year, maybe 10,000 feet thick. And so they realized that the Earth was tens to hundreds of millions of years old. Just about everybody believed that in the 19th century. Okay, and here's our favorite spot, the Grand Canyon. How many of you been to the Grand Canyon? Yeah, I was here for like 20 years before I visited the Grand Canyon. Very embarrassed to say that. But finally I went and visited it. It's an amazing place. But the Grand Canyon and the Colorado Plateau are an example of 10,000 foot geologic formations constructed from layers of sediment. And the Grand Canyon shown here is just the lowest part of what's called the Grand Staircase of the Colorado Plateau. So the thickness of the Grand Canyon is about 5,000 feet, meaning it's about 5,000 feet to get down to the bottom, and you're going through geologic layers the whole time. But then the Colorado Plateau, which also includes places like Zion National Park and Bryce Canyon National Park, those go up another 5,000 feet in geologic layers. So there's a total of 10,000 feet of geologic layers in the Grand Canyon. And I made this video here, this link here, about the Grand Canyon and about the way that the limestone and sandstone layers were laid down. I actually have 1,000 views on this video. I wasn't planning on that because, it's pretty boring and it's just like going over the layers, but I guess people are interested in that. But for example, I talk about how the limestone layers are laid down as a result of the death of marine creatures who have shells made of calcium carbonate. And none of the type of limestone in the Grand Canyon and across the Colorado Plateau, for that matter, or any other limestone, forms in a flood, like Noah's flood, So anyway, it's just good to look at the present ways that things are laid down. And you can see that these ancient formations have the same characteristics. And so we can assume that they were laid down in the same way. Well, prior to the 20th century, because of the thickness of these formations, scientists knew that the formations were very old, but they didn't have a reliable time scale. But in the early 20th century, Ernest Rutherford discovered decay rates of radioactive materials, such as the decay of uranium to lead. And by looking at the ratios of uranium and lead, scientists realized that they could determine the ages that rocks solidified. And that was popularized right after Rutherford discovered this radioactive decay. Bertram Boltwood compared lead and uranium levels in rocks collected from around the world. And so he was able to compare the ratio of the parent product to the uranium to the daughter product lead in order to date the rocks. And remember from our discussion of chondrules that the date is the date that the rock solidified. So that's day 0. And so scientists have derived many methods to use other parent and daughter isotopes to date rocks and even biological materials. And many geologists have become experts in conducting analyses of rocks and are able to derive progressions such as the ages of these layers at the top of the Grand Canyon and also the entire geologic timescale here. So now they have precise dates for the entire geologic timescale. And I actually knew a guy here at the University of Arizona, and he showed me his instruments and talked about what he did. It's a very complicated thing. As you can imagine, with ancient rocks, you have lots of factors, and you have to account for all those factors. And you maybe use several methods to confirm that your analysis is correct. And so with those methods, for example, this is the Kaibab Formation at the top of the Grand Canyon. The date errors within the range of 2 to 5%. Okay, so there's a few rocks on Earth that are older than 3.85 billion years. Or there are few rocks on Earth that are older than 3.85 billion years. And remember we talked about planet migration a couple times ago. But in this case, here are the planets, including Uranus and Neptune, and we don't count Pluto anymore, so we don't have to think about that. But they were all kind of clustered in the inner solar system, and then we had all these planetesimals in the outer solar system. This is called the planetesimal belt. But at one point, Uranus and Neptune moved outward, And you can imagine as a planet moves outward and encounters a planetesimal, it's going to throw the planetesimal into the inner solar system. And so all those planetesimals entered the inner solar system and either hit the Earth or went into the sun or went out of the solar system, or actually maybe they went out of the solar system the other direction. So that caused what was called the late heavy bombardment about 3.85 billion years ago. And so that actually melted the Earth's crust and almost all of the crust, I think. But there's still a few locations with rocks that are from the Hadean before this happened. So they have a few of those. But there's almost no rocks from the Hadean. So we don't know a whole lot about the Hadean Eon, which is why we're not starting there. Anyway, that was a good thing to happen in the long run, because now we have no asteroid impacts, or almost none. I think, every 10 million years or so, every once in a while they hit a really sensitive spot, like, an oil formation, and almost eliminate life on Earth. But in general, we have a pretty stable climate. And another benefit to that is all those asteroids added heavy elements to the Earth's surface. I didn't talk about it before, but the heavier elements moved to the center of the Earth during the period called differentiation. So we wouldn't have had those heavier elements at the surface if not for this late asteroid bombardment. Okay, and here is the oldest rock on Earth, except for zircon crystals. And this is from the Acasta Gneiss complex in Canada. And it's 4.03 billion years old. So it's about 200 million years older than the beginning of the Archean. So this survived the end Cretaceous extinction. It's called gneiss. It's a metamorphic rock that formed under high pressure and temperature. Okay. Okay, so here's a graph, very nice graph. So using rocks collected from the Archean and Proterozoic geologic formations, scientists are able to determine such things as water temperature, atmosphere composition, and ocean chemistry. And they know that certain types of rock in the modern world form in certain environments. So just like I mentioned before, we had the formation of limestone. We know that that was formed in the same way before. They're able to look at rocks in the ancient geologic formations, and based on how they know rocks form today, they're able to make deductions about what the conditions were when those rocks formed. So this graph shows ocean surface temperature, atmospheric carbon dioxide, oxygen, and methane over the Archean, Proterozoic, and Phanerozoic eons. So here you can see the ocean temperature in the Archean when the sun was colder, and you can see it's about 26 degrees centigrade, which is way above freezing point. So that's based on rocks, So like I said before, that's the faint young sun paradox. And then these gray bars, they represent glaciations. So you had a rise in oxygen at the beginning of the Proterozoic, and that's what triggered these glaciations. So the global warming potential went down. And so here you have these two glaciations at the beginning of the Proterozoic, and you have these 2 or 3 glaciations at the end of the Proterozoic. There wasn't really a change of oxygen prior to those glaciations, but there was possibly a decrease in carbon dioxide and methane. So maybe that's what triggered them. I really don't know. All of the glaciations in the Proterozoic were equatorial. Well, at least that's what I think. But others would say that the entire Earth was covered by ice. There's just no evidence of ice at the poles in the Proterozoic. And then all the glaciations in the Phanerozoic, which is our current Eon, were at the poles, as we know. So there's still polar glaciation. Here's the interesting line. You can see this diagonal line is the solar luminosity. So you can see that it's increased from the Hadean, actually since the sun formed, up to the present time. And also here's the line that reflects the asteroid bombardment of the Earth. And so you can see that there was this huge asteroid bombardment at the beginning of the Archean. And now it's pretty much dropped to zero. You know, we do have some, maybe every 10 or 20 million years. We had one relatively recently, but it didn't hit a part of the Earth that was, by relatively recently, I mean like 6 million years ago or something. But it didn't hit a part of the Earth that was sensitive, that would have caused a global winter or anything. So scientists can learn a little bit about the Hadean Aeon from zircon crystals that form when lava cools. And the reason for that is they're extremely durable and they've survived in places where other rocks haven't. So they didn't melt when the rest of the crust melted. So the main ones, I think, from the Hadean Aeon are in the Jack Hills in Australia. Okay, so the Archean Aeon, and here we have the universal time scale, or geologic time scale. So here's the beginning of the Archean. So we're looking at the beginning here in the Eoarchean. And so that began right after the late heavy bombardment. And likewise, chemical evidence indicates that life began in the early Archean. And this would be most likely since the atmosphere was extremely reduced after getting bombed by these asteroids that were high in organic matter, like methane. So methane would cause an extremely reduced atmosphere. And that only lasted for like 1 million or 2 years. And so life needed to evolve in that span of time. Because as soon as the atmosphere was slightly or less reducing and maybe slightly oxidizing, any forming biochemicals would be destroyed by oxygen. So I think it's likely that if life did evolve, that it evolved within 1 million or 2 years, at least got its start. So that's an interesting field of study that scientists are looking into. Okay, and then also if the atmosphere was reducing, some scientists think that the atmosphere might have been something like this orange Tholen haze, similar to Saturn's moon Titan. So with that reducing atmosphere, there might have been this haze that formed in the atmosphere. And only 10% of the light might have reached the Earth's surface. But photosynthesis can occur in that low amount of light. Scientists have proposed that possibly this would be a solution to the faint young sun paradox, you know, that it have a high global warming potential. But I think I read that the problem with this one was that the top of the orange Tholen haze would reflect the sunlight back into space. So it really wasn't a solution. And so the way that scientists evaluate these things is they do an energy balance. And so they know like how much sunlight's coming in, how much infrared radiation is leaving the Earth, how much is being absorbed by the atmosphere, how much is it being emitted back to the Earth by the atmosphere. And so they set up these energy balances, just like today with calculating the global warming potential. The thing that causes global warming is if there's more carbon dioxide in the atmosphere, it's reducing the amount of energy that can leave the Earth's atmosphere, and methane as well. They occupy spaces in the energy spectrum that aren't occupied by other chemicals. So they realized this like back in the 70s. They said, oh, the Earth atmosphere is going to heat up because you're putting carbon dioxide out into the atmosphere. So anyway, there's more in the chapter on the global energy balance and global warming and things like that. Okay, well, here is what I talked about before with the axis tilted over, where I've already mentioned this, so I don't need to spend any time on it. But if the sun was shining on one side of the earth, the waters would be heated up. And so that would explain why there was liquid water on earth. Okay, so then there was the great oxygenation event at the end of the Archean Eon. I think I mentioned before that photosynthesis evolved. And some leading scientists think that the current, photosystem one, photosystem two system, the complete photosynthetic system, had evolved in cyanobacteria by the end of the Archean Eon. And that's what oxidized the atmosphere. And so that's been called the Great Oxygenation Event or the Great Oxygenation Crisis, depending on your point of view. If you were Archaea, who needed a reducing atmosphere to survive, it would have been the Great Oxygenation Crisis. Okay, and then these are probably mounds of algae and bacteria. So they find these stromatolites in geologic formations where cyanobacteria grow, and then bacteria grow on top of them, and I guess eat them, and then cyanobacteria grow on top of them. So they build up these huge mounds. So I think that's what you're seeing in this representation of the Archean Eon. And also the moon was much closer on the early Earth. So that's why the moon looks so big here. Okay, so there's a couple of different places where they find rocks from the early Proterozoic and late Proterozoic. And one of them is this location here in Canada. It's the Gowgonda Formation. And it's at the northern end of Lake Huron, which is one of the 5 Great Lakes in North America. You can see this is the border of United States and Canada. So in this little location here, there's rocks that are sticking up from the early Proterozoic where they can see that there was glaciers. And this link is to a video by a geologist who's clearly excited about his investigation of the Gowgonda Formation. I really liked it. And he does a really good job explaining just how they know that there was glaciers there. So here are some rocks where they can see evidence of glaciation. So glaciers move over the earth and break up the rocks that they're moving over. And actually they lift up other rocks and polish them as they're grinding over the earth. And so then they can see that the rocks are then deposited, like these rocks. You can see that this is a broken up rock that was then deposited in some other soil or rock or something. And so they can determine characteristics of the glaciers and the rocks they were passing over by looking at this. And so this is from that Gowgonda Formation where you can watch that video from the geologist. He'll explain everything. Okay. And then here's another example. So when the glaciers move over water, water has silt in it. And so then they drop the rocks into the water, and these are called drop stones. So there's a couple different locations where they find these evidences of glaciations. And in this lecture, I'm mostly focusing on the ones in Canada from the early Proterozoic, but most of the text has pictures from the late Proterozoic and from that guy, George Williams, who I mentioned earlier, who came up with the holist hypothesis. Another thing that they can see, evidence of glaciation is, that they just leave striations over the rocks as they move over them. So they can see where the glaciers moved over the rocks. Okay. So the sites at the northern end of Lake Huron show glaciations that were between 2.4 to 2.1 billion years ago. And here's an interesting thing. So the glaciation occurred between 2.4 and 2.3 billion years ago. There's also a technique called paleomagnetism, where they can look at the alignment of iron in the rocks And they can see what latitude the rocks were at when they formed because, with Earth's magnetic field, the iron in the rocks will line up in a certain direction. And so they know how the magnetic field comes out of the Earth. And so they can tell exactly where on the Earth these rocks were, not with respect to latitude, but with respect to longitude, distance from the equator. And so these dots show the paleolatitude of the Huronian glaciation and when it was glaciated. And you can see that it was glaciated when the rocks were within 15 degrees of the equator. So that's an indication. And then they weren't glaciated afterwards, even though there was glaciations up to 2100 or 2.1 billion years ago. So this is an indication that the glaciations were only occurring at the equator and was not covering the entire world as in snowball Earth. Okay. So I was interested to see what's been going on with these theories. And I found this paper from 2024 where this lady used what are called detrital zircon records. So what detrital zircon records are, and that's the paper down here I'm referring to, just came out. But she was looking at these rock formations in Canada. The one I was showing you was in the Superia supercraton, and then there's others in the Sclavia supercraton. But anyway, she used what are called detrital zircons. And what that means is the lava comes out, the zircons form, they get eroded away, and they get washed down the hill. And then they look at those and they determine certain things. I don't know what, but geologists could have methods to determine like how they formed, where they formed, and all sorts of things. Okay. So a craton is like a solid part of the continent or of the tectonic plate. So for example, now we have the South America craton and the Africa craton, or not now, but in an earlier time. And they had these certain parts of the craton that were sticking out above the water, the ocean. Okay. So here's the supercratons model or the supercontinents model. At the time of the formation, you can see that they have other glacial sites in that location. And you can see that all the glacial sites are towards the equator, but they're not up here. So they know their paleomagnitudes were, and the glacial sites are only near the equator, not up here. She proposed a different model. I don't know what she was talking about. I mean, I'm not because I'm criticizing her, but I'm just not a geologist. And she said, well, maybe Sclavia was over here and Superia was over here, supercraton. Although it really doesn't matter, I don't think, with respect to latitude, because she still has them at the same latitude. She's just saying that maybe it's over here and over here. Anyway, she had reasons for saying that, but we still have all the glaciations near the equator and not near the poles. Okay. So this is her paper and the conclusions. And I just wanted to read these two quotes from her. Low latitude glaciation, that means glaciation at the equators. The presence of low latitude glaciation may be explained either as an episode of global glaciation, and here's the guys who have promoted that idea, or a period of high obliquity, and here's George Williams, 1998. He actually proposed it in 1975. But anyway, so the high obliquity hypothesis, that's the idea that the axis was tilted, suggests a high obliquity degree, 49 to 54 degrees, between the magnetic field and the spin axis, proposing that equatorial regions were colder during the Proterozoic. The high obliquity theory is positive to have occurred due to massive bolide impact. So like when the moon formed, something hit the Earth and tilted its axis. that favored mechanism for lunar origin. Therefore, high obliquity may have prevailed during the Precambrian with low paleolatitude of glaciations in the Paleoproterozoic and Neoproterozoic. However, a dynamical mechanism is required to bring the obliquity down to its present value of 23 degrees. So that's our current axis. And this mechanism is unknown. That's the primary, or that's a big reason people don't embrace this theory, because they can't explain how the Earth's axis tilted. Okay, and then she goes on, the lack of Sclavian glaciogenic sedimentary rocks, or lack of glaciers in those Sclavian places, coupled with paleomagnetic data and compiled uranium-lead detrital zircon, points towards two hypotheses. The Paleoproterozoic glaciation was regional in nature and not global as presumed by previous research, so not snowball Earth. Or Sclavia was largely submerged during the Paleoproterozoic glaciation, and for this reason, it does not record glacial deposits. So she's saying that those northern places were underwater, which is why they didn't show glaciers. So given the requirement of a degree of orbital high obliquity to explain the low latitude glaciation on Superia and the lack of dynamical models to account for this, so she's saying, because we can't account for how the Earth's axis changed, we're not going to go with that hypothesis. We're going to go with the idea that there was a global snowball Earth. So we find the latter hypothesis to be most likely, which is snowball Earth. Okay, that's a very interesting paper. Okay, I don't have hardly any time to go into philosophical and religious perspectives on climate, but I just want to mention one thing. So Moses' fourth day, then God said, let there be lights in the expanse of the heavens to separate the day from the night, and let them be for signs and for seasons and for days and years. If the solar system is the expanse of the heavens, and the sun shifted into that position rather than a different position, then that would cause seasons, days, and years. All right, we'll see you next time.